Okay. Right. Yeah, so the topic for this week was week 5. It was neural networks. So I will be like I have done in the previous iterations. I would be going through the questions that were there in the last year's assignment for this for this particular topic, and I'll go over them. The questions are pretty simple, and if you have any doubts in between, you can stop and ask me, and I will be happy to answer those. Okay, so I'll start. Okay, so I'll start. The first question is, if the step size in the gradient descent is too large, then what can happen? The first option is overfitting, the next option is the model will not converge, and the third option is we can reach maxima instead of minima. So if you see here, I mean, if this is your loss function, and suppose you are at this particular point which I am marking out. Okay, yeah, which I am marking out here, and suppose the gradient descent is asking you to take a direction in this a step in this particular direction, and and you have a very big step size, then what can happen is you can go directly here, and then from here the gradient will ask you to move towards this particular direction. You can move here, and so on and so forth. And this is the minima that I am marking out, maybe in black. This is the minima that you can reach. So that is one possible way. The other way, but this will lead to many oscillations. So this is one possible reason. I mean, this is one possible way in which you can see, in which you can understand your the step size of your gradient descent being very large. The other way is, suppose in the same context, if you have a bigger step size than the one which I just showed on the left, I mean, with respect to this, if you have a bigger step size here, then what can ideally happen is, I mean, what can probably happen is you will move somewhere here in that case, right? And again, if you have a very big step size, the gradient will ask you to move in this direction, but if you take a very big step size towards the left, what will happen is you can move towards the left like this, and you can see that like this was moving in this particular direction, this can move in the exact opposite direction, right? And so in this way, what will happen is the model will not converge in this particular case, and so that is a possible drawback of a very big step size in gradient descent. Okay, so that's the first question. The second question is, recall the ZOR tabulated below. So this is the truth table that has been given for the ZOR function, and where we did a transformation of features to make it linearly separable. So one transformation of features was probably shown in the class. Which of the following transformations will also work? So there are 4 given transformations, out of which we have to say that in which of the 4 cases this particular case, I mean, these particular 4 points, they become linearly separable based on their class. So let's go over them one by one. So the first case is when I have x1 hat equal to x1 square and x2 hat equal to x2 square, right? So let me draw the values of x1 and x2. So x1 will be, for the first case it will be 1, x2 would also be 1, and y equal to 1, right? For the second case, x1 hat would be 1. So basically, so since you are taking a square, all of them will essentially become equal to 1. Sorry, this will be -1 and this will be -1. These are the two classes that you want to separate out. You want a linear classifier such that the first 2 points, like this, the first and the last point, these 2 points, they belong to one particular side of the linear boundary, of the linear line of the line that you will be drawing, and the other two, like this one and this one, they will fall on the other side. Now if you see here, all the 4 points are becoming the same in the first transformation that has been given, and therefore this can't be linearly separable, because all of them have become the same point. All the 4 points have become the same point, and therefore this can't be linear. It can't be linearly separated by the first feature transformation. The first one is not possible. Now let's look at the second one. The second one is okay, I'll just rub the first one off. Yeah, I hope the first one is clear. So I will be rubbing this off, and I will move and I'll be doing the second one here because of okay, let me keep it. And one thing which I'll do is maybe I'll move this B here. Yeah. Now let's say I have x1 prime equal to 1 plus x1 and x2 prime equal to 1 minus x2, and I have y. So y is same, y minus 1 1 1 minus 1. What is x1 hat? X1 hat for this would become 0, and this would be 1 minus of minus 1, so it will be 2. The second one would be 1 plus 1, so it is 2, and that is 1 minus of minus 1, so that is also 2. The third one becomes minus 1 plus 1, so it is 0, and the other one is also 0. x2 hat is also 0 for the third case, and the last case is 1 plus, so that is 2, and 1 minus of 1, so that is 0. So these are the four new points that I have got. Now let's just plot them and see where the 4 points are. So one is at 0 comma 2, so somewhere here. So this is the x2 hat axis, and this is the x1 hat axis. Okay. So the first point is 0 comma 2. The second point is the first point is 0 comma 2, right? Yeah. So the first point is 0 comma 2, so it will be here. The second point is 2 comma 2, so that is here. The third point is 0 comma 0, so that is here, and the last point is 2 comma 0, so it is here. So there are two sides of the square. Now you see what is, now let's mark the two classes. So the first and the third point, so 0 comma 2, which means this particular point, and 2 comma 0, which is this particular point, they need to be in the same class. They need to be on the same side of the line that you would be drawing, and the other two will need to be on the same side of the line that you are drawing. And you will find and it is not possible for you to separate out these. I mean, you cannot find any line which will have 2 of the blue points on one side and 2 of the black points on the other side. So the second option is also not correct. So the second option is also not correct. So let's look at the let's look at C. So okay, C I will maybe draw here, that will be easier. So let's say x1 hat, this is x2 hat, and this is y. So for the first one, x1 hat would be 1, and x2 hat would be minus of x1 x2. Okay, so it is always minus 1 of this. Okay, then this is minus 1 1, this is minus 1 1, the last point is 1 and minus 1. These are the 4 points, and these are the 4 labels. These are the 4 labels. So now for C, if you draw, then C I am drawing here. So C, if I draw, then what happens? The first point is at 1 minus 1, right? So 1 minus 1. So the first point is here. Maybe I will directly mark in black. First point is here, and the last point is at 1 minus 1. So it's at the same place. So the first, if you see the first and the fourth point, they have actually coincided and have come up to be 1 and minus 1. Let's draw the two blue points. They are both at minus 1 comma 1. So minus 1 comma 1 is here. So now if you draw a line like this, then you will see that this is the linear, I mean, consider this as a line. This has become a block, but consider this as a line. Let me just draw it like that. Consider this as the classifier that you wanted to draw, that you want, and you see that the two blue points and the two black points, they are on opposite sides of the linear classifier, and therefore XOR becomes linearly separable by this transformation. So C is definitely a correct answer. Also, if you work out D, I believe that will also come out to be correct, but let me still, okay, this is hung for some reason, I don't know why. Okay, so D I'll draw here, maybe x1 hat equal to x1 minus x2 whole square, and x2 hat equal to x1 plus x2 whole square, and this is y. So x1 minus x2 whole square, so the points are, see, x1 minus x2 whole square, right? So so whenever x1 and x2 they are equal, that means x1 hat will be equal to 0 and x2 will be equal to 4, right? So that means x1 and x2, whenever x1 and x2 is equal, that means this will turn out, the first and the third and the last points will turn out to be 0, and the corresponding x2 hat values would be 4. And similarly, the first, whenever x1 and x2 are opposite, I mean they are, one is 1, the other is minus 1, then x1 minus x2 would become, x1 minus x2 whole square would become 4, and x1 plus x2 whole square would become 0, and therefore this would be 4, 4, 0, 0. Clearly from here you can, I mean you don't even have to draw anything, you will be able to understand that, this is these, again this would become linearly separable, but I'll still draw. So the first point is at 0, 4, which is somewhere here. The fourth point is also at 0, 4, and the other points are at 4, 0. So other 2 points are at 4, 0, and now if you draw a classifier again like this becomes linearly separable, right? So the options 3 and 4 are correct in this particular case. Okay, I hope I was clear. Right, so for the third question, the question is, okay, so the third question is, what is the effect of using activation function of fx equal to x for the hidden layers in an ANN? So if you have gone through the lecture of ANN, you would understand that the main contribution or the main way, I mean the major reason why neural networks are famous even today is the fact that they can build up arbitrarily complex functions, and the main reason for that complex function, or for being able to build up that complex function, is the introduction of nonlinearity. So if you don't have any nonlinearity, because fx of x is a linear function, then ANN is effectively becomes equivalent to doing a multi-output linear regression. Why multi-output? Because to the final layer will have multiple nodes, and therefore each of them will give out some real values, and it will be like you are doing some feature transform, you are doing some feature, you have taken some input features, you are multiplying them with some matrix, and you are giving out some output. If you don't have any nonlinearity, then that means you are just doing normal linear regression. So ANN, so the other options are of course not correct, because we can, it is so the first option is of course not correct. It will obviously have an effect if you don't have any nonlinearity. Backpropagation will always work even if you have a nonlinearity. Backpropagation will only fail if you have something which is not differentiable. Fx of x is differentiable with a derivative of 1, and therefore that won't cause an issue. And we can model highly complex nonlinear functions is of course not possible, because you don't have any nonlinearity in your network. Therefore only the option 2 is correct, which means that ANN is equivalent to doing a multi-output linear regression, right? Okay, so the fourth question is, which of the following functions can be used on the last layer of an ANN for a classification? So the options are softmax, sigmoid, tanh, and linear. So consider this as your output node, and this as your input. So let's say this is z, and this is your f of x, right? So this f is the activation function. I mean, these f can be any of these four particular things. So let's say if you are, but if remember that you are doing classification here. So classification means your model needs to predict something between either 0 1 or minus 1 1 or something of that sort, right? And therefore softmax is correct, because softmax is something like it will take so softmax gives you at the output, softmax gives you a probability, so that always lies between 0 and 1, and you can say that if the probability of something happening is greater than 0.5, then I will classify it as 1. If the probability is less than 0.5, I will classify it as 0. So softmax is definitely a correct option. Sigmoid is generally always sigmoid is also used for the same reason. It will always give you a value between 0 and 1. Tanh can also be used, because tanh, as far as I remember, it gives a value between minus 1 and 1. Therefore you can say that anything which is above 0 belongs to a particular class, anything which is below 0 belongs to the other class. So that is tanh. However, if you do a linear class, if you to put a linear activation function at the end, then what happens is you have no control over this z value, and therefore fx will be that particular value. So if you have a value of 10 here, you will get a value of 10 here. If you have a value of minus 10 here, you will also get a value of minus 10. Similarly, if you have a value of 100, so 10,000, you will have a value of 10,000 here, and therefore this particular output of this particular scheme of outputs won't fit well with a classification task, because in classification you will have to say that either this particular input belongs to this class or to the other class, and therefore linear is not a correct option. However, you can use softmax, sigmoid, or tanh. Okay. The fifth question is, threshold function cannot be used as an activation function for hidden layers. If you understand, I mean, if you use linear, if you use neural networks, you will find the threshold function is never used as a activation function for linear layers. But why is it not used? It is not used because it is if you have this sort of a threshold, okay, above something it gives a value of 1, let's say. If it is this sort of a function, then you will never use this sort of functions. So the first, so the easiest, so of course this is a nonlinear function, right? This is of course a nonlinear function. If it is a nonlinear function, that means that threshold functions do not introduce nonlinearity is a wrong statement. So the reason is definitely false, but the statement is true. Now there can be multiple reasons as to why this is not used. The first obvious reason is, and I think that is enough for this particular course, is to see that this function you see is not differentiable. It is not differentiable at this point, and therefore this function cannot be used. I mean, backpropagation would fail when it tries to look at this particular point. However, there are other reasons. I mean, there is a very common function which is also not differentiable at one particular point, one particular activation function which is widely used even today, which looks like this. This is known as rectified linear unit or ReLU function, but ReLU is almost always used in all neural networks even to this day. However, this is also not differentiable. So you must understand that there is something more that is going on here. It is not just non-differentiability that we look for. We also look for something which is more than non-differentiable. Let's just put it at the let me just state that, but going beyond that reason is probably out of this course, and therefore I will not tell that. So the reason that you can keep in mind for now is backpropagation cannot be applied through this particular non-linearity, and therefore and therefore statement is true and the reason is false, right? Okay. The next question is, we use several techniques to ensure the weights of the neural network are small, such as random initialization around 0 or regularization. What conclusions can we draw if weights of our ANN are high? So if your model is overfitted, then your weights in most cases will be high, but it is not the other way around. If your weights are high, then you cannot say that your model is overfitted. There is a link between high weights and the model being overfitted, but you cannot always say that whenever your weights are high, your model has overfitted. Maybe your model has required those weights to be high even to generalize to the but it generalizes very well to the test set. Okay. So model as overfitted is something which you would feel that it is correct, but it is actually not, because whenever weights are high doesn't mean that your model is overfitted. However, when model is overfitted, in most cases your weights would be high. It was initialized incorrectly is something which is I mean it doesn't make any sense here. So even if it is initialized incorrectly, it doesn't tell us the way, it doesn't tell, I mean it won't one thing is of course you can do something like you can start your weights to be very high. I mean you can initialize your weights to be very high, but even then we use several techniques to ensure the weights are small. So generally it has been said here that random initialization around 0 or regularization. So it means that your weights have been started with a random initialization around 0, and therefore that is a correct initialization, and therefore it is not the correct option. At least one of A or B is also not correct, and therefore none of the above is the. So basically just by looking at the neural network weights of a trained neural network, it is very difficult to understand whether your model has overfit, it has underfit, or it has gone or something has gone wrong. You only have to look at the validation set performance, and only then you will understand what is happening with your model. Okay. Overfitting and all those things can't be found out by looking at the weights of the neural network. Okay, then comes on different initializations of your neural network, you get significantly different values of loss. What does that mean? You see what happens with neural networks is the loss. Okay, so there is a concept of a loss curve. So what do we mean by the loss curve? So let's say I have just a single weight, I vary that weight, and what happens is the error of the neural network goes like something like this. Maybe it can be arbitrarily complex. Neural networks can generate very complicated error field which may not be even convex. So this is not a convex curve, right? So if you have such a curve, then you see there are multiple minima lying in this curve, like this is one minima, this is one, or multiple local minima. This is probably the global minima, but these are all local minima, right? Now on different initializations, so let's look at this particular place. On different initializations, what can happen is, so let me draw it in a zoomed out manner. Okay, let me let's just think that this is drawn in a zoomed out manner like this. Now suppose if you start from here and if you go here, your gradient descent, you have taken very small step size and you have gone here, then that means this is the point that you would end up in. Once you have reached this particular point, it would be very difficult for you to move out of this, and therefore this is one value where you can settle. Okay, then this is W here. Okay, and this is one, and this is the error or the loss. So error and loss are the same, and this is the particular point that you have ended up with. Suppose you had started here, then you would have ended up somewhere here, right? If you had started, let's say, here, you would have ended up here. So you see that depending on where you initialize your model, you might reach completely different points with completely different loss values, and the reason for that is you have multiple local minima in this particular, you have multiple local minima that is appearing in the loss curve, and depending on where you start, you can reach one of them, any one of them, and therefore if you can have significantly different values of your loss, and therefore option D is correct, multiple local minima. Okay, then the likelihood L theta of x is given by, so that this is a simple definition of likelihood function. So likelihood is like, if you want to remember this in English, it's like what is the value of theta that is most likely to have generated x. So for likelihood, just from the English term, it is like theta is your unknown. So what is that value of theta for which the likelihood of my data or the probability of my data getting generated is maximized? So if that is the case, then you would understand that this is the correct option, and that means that given theta, probability of x, okay, given theta, what is the probability of generating x? So that is the likelihood function. So option 2 is the correct one here. The second one is a very simple application of likelihood. So maximum likelihood estimate. So you are trying to estimate the probability of it raining today using maximum likelihood estimation. Given that in n days it rained nr times, what is the probability of it raining today? So you can say that if you have an idea of maximum likelihood, you would I mean, this is pretty simple, like, right, that if it is n days and out of which it has rained nr days, then what is the probability of it raining on a one particular day, and that is nr by n. So that is the maximum likelihood estimate that you have. So this is like saying that if I have tossed a coin 100 times and probability and head has come up to be 60 times, then probability of head is 60 by 100, which is 0.6. It is a similar problem to that, where n, this is n, this is nr, and this is probability of rain, and therefore this is nr by n. Okay. So the last question is, choose the correct statement. Multiple may be correct. So MLE is a special case of map when prior is a uniform distribution. MLE acts as a regularization for map. MLE is a special case for map when prior is a beta distribution, and map acts as a regularization for MLE. Okay, so let's see. Your unknown is always theta, right? So this is what you want to find out. You have x and you want to find out theta. This is your unknown. Theta is unknown. This is known. Now what you do is, you can, by Bayes rule, so I hope everybody of you is aware of the Bayes rule, but so this becomes p of x theta, right? Okay. Now what you need to do is, your unknown is only theta. Your unknown is not x. X is given to you, and therefore you don't need to consider this particular term, right? You just need to consider the numerator. Now yeah, if you see the likelihood, what I had written, L of theta given x, which is actually p of x given theta. So you see p of x given theta is appearing here. So this I can write as p of L of theta given x, which is same as p of x given theta, into p of theta. The denominator I am ignoring because theta is not present there. Now if you forget this, if you completely forget this, then this becomes your MLE estimate. This becomes your MLE estimate. But if you consider this also, if you consider both of them, that becomes your MAP estimate. Now always remember one thing, that you are trying to take maximum over theta, sorry, you are trying to take a maximum over this L theta given x into p of theta, and when you are taking that, and so when will L theta given x, when you are maximizing over theta, when you are maximizing with respect to theta, oh sorry, this will be argmax because you are finding out theta, right? Okay, so when you are finding out the theta for which this particular value is maximized, and you have to take p of theta into account. However, you want this to become exactly equal to this particular term. Because that is the first question that has been asked. So, you take options either A or C would be correct. So, ML is a special case of MAP when prior is a uniform distribution or a beta distribution. So, beta distribution is a complicated distribution, so you don't even need to remember that for solving this problem. So, what happens is you need to know that L theta given x into p theta, the argmax of that and L theta given x would be the same. When would that happen? When p theta is same for all the theta. P theta is invariant to theta. Whenever theta changes, p theta doesn't change. Only then L theta given x into p theta and L theta given x will give out the same solution for argmax over theta, right? And therefore, and this happens, which distribution gives this? If you have a distribution, I am showing it in the discrete case, if you have these many values of theta, let's say, and all of these values have the same, and for all of these values of theta, the distribution gives you the same probability of that particular value of theta occurring, only then you will feel that okay, then this is just so it is invariant to theta, because whatever values of theta I am selecting here on the x axis, whatever value of theta I am selecting here on the x axis, I am getting the same value on the y axis, and therefore this particular distribution is known as a uniform distribution because it gives all of them equal values, and therefore the first option is correct. If the first option is correct, the third option can't be correct. So that is one. The other is MAP acts as a regularization for MLE. Now you see, if I again write the MAP estimate formula, I am writing in terms of probability only, right? So what is happening here? So what is happening here is you maximized this p of x given theta as part of maximum likelihood estimate. However, I mean log function, you can take a log function of this and then this product will separate out, but okay, let's leave that for now. However, for that particular theta, what you are trying to do, so when you are just trying to argmax over p of x given theta, that means you are trying to find out a theta with the one objective only, that is maximize the probability of getting x. However, if you also put a p of theta into this, then what happens is you say that okay, p of x given theta can be maximized as is, that is fine, but at the same time I don't want p theta to be something completely different, right? I have certain belief about p theta. So let's say you have I mean, I'm just drawing a value, this is just for your reference, this is not correct in the true sense of how p of x given theta might look like. So for example, if you have a p of x given theta um, uh, okay, so okay, let's not draw because it might confuse you. So let's say I'm taking the head and tail example. So I have taken a coin, I have tossed it 100 times, I have got 60 heads, and the probability of head I have got out to be 0.6. That is the MLE estimate. That is, this is nothing but P of x given theta. When you try to maximize this will come out to be 0.6. That is one. However, let's say you have tossed this coin 100 times and for some reason 90 heads had come. Then your probability of head would be 0.9, right? Because that is how you have calculated the MLE estimate. However, at the same time you knew from beforehand that the coin that you had started with, itself was fair. I mean, you had a fair, as you had an assumption that the coin was fair. It was probability of head and probability of tails equal to 0.5. You had this assumption. For some reason, 9 out of 100 tosses, 90 heads might have fallen. I mean, that is a probabilistic thing, so it might fall. However, you have had this belief that this was 0.5. Now you see where regularization comes in from from machine learning perspective. What does regularization mean? Regularization means it is used for solving the problem of overfitting. Now what is overfitting? Overfitting is if your model fits to the training data so well that it has fit your training data so well that it is performing very poorly on the test data, right? Now if you translate that same idea into this particular example that I am just showing you, then what is happening is if you just take the MLE estimate and if it fits well, how does it perform badly? Yeah, if it fits well on the training data, then it will perform badly. It might perform badly on the test data. I'll give you this example only. So let's say your training data is 100 tosses, out of which 90 have come up to be heads. Your MLE estimate would give you a value of 0.9. This means that you have trained your data. So this you can think of if you have to think of the machine learning perspective, then this is like fitting your training data perfectly. So you have fitted your training data perfectly, and now you have come up with a estimate of your probability of your coin giving out heads as 0.9. If your coin was actually fair, and for some reason out of 100 heads, out of 100 tosses 90 heads had come up, then is 0.9 a very good estimate? Now suppose somebody comes and tosses the coin again and asks you, what do you think is the probability, what do you think will be the probability of heads falling? Now that in machine learning term is your test data. You will say, because you have found out 0.9, you will say it will fall heads with a probability of 0.9, and then since your coin was actually fair, your prediction is absolutely wrong, because it might not fall, because it might be completely so you have fitted your training data so well that let's say the person comes and tosses your coin 10 times, 6 times it falls heads, 4 times it falls tails, and then your prediction of 0.9 is completely wrong. So here the information that you are actually missing out on is your prior probability. So what was your prior probability? Your prior probability or prior belief. The reason why it is called prior belief is you had some idea about how about your coin, and that is a prior belief that you had even before performing the experiment, and because of that this 0.5, if you look at the lecture, it's a complicated calculation. I'll not go through it, but it's so if you have a beta distribution and so on, so this, if you take this prior distribution into account of 0.5 heads and 0.5 tails, then you will see that this probability of head will be high. It will be higher than 0.5, but it will be much lower than 0.9. It will come out to be, let's say, 0.75. I don't know. I mean, after beta distribution it will come out, let's say it comes out to be 0.75. So with this particular prior belief, what you will now tell, now suppose a person comes and you will tell, no, My MLE estimate had given me 0.9, but my initial belief was that my coin was perfectly fair, and therefore my updated estimate or MAP estimate, this is known as maximum a posteriori estimate, my MAP estimate is 0.75. And now when the person tosses and he or she gets 6 heads or 7 heads out of 10 times, we'll say, yeah, your estimate was probably correct. Your coin was probably, it is giving out a head of 0.75 with a probability of 0.75, right? So if you can pick out that analogy which I just told, then you would understand that MAP is acting as a regularization for MLE estimates. So MLE estimate is something which you want that theta for which your training data distribution, you are trying to maximize the probability of seeing the training data distribution. MAP also puts the prior into the picture and says that, okay, you are seeing that data, that is fine, but I had some prior belief about the parameters, and therefore I would ask you to regularize or tone down your results a bit so that it generalizes well on the test data. Therefore MAP acts as a regularization for MLE. Okay, I hope that is fine. Somebody has had a question, so I hope the doubt was cleared. Yeah, Shashikant, your doubt was clear, right? Do you still have the doubt? Okay, I don't see any messages. Okay, yeah. So with that, we come to the end of this set of questions. If you have any doubts, you can ask me, or else I'll close the session. Any doubts from anybody? Yeah, sorry, I lost my connection for some time. Let me see. Yeah, do you have any more questions, or else I'll stop the session? Okay, if there are no more questions, thank you. I'll end the call for everybody. We'll meet again next Saturday.